So welcome, folks, to another one of our HDR UK Applied Analytics seminars. Usually I introduce people for these seminars, but for the first time, I'm doing one with some trepidation. So I have to introduce myself. So I'm Dave Robertson. I'm a prof in computer science at Edinburgh. I'm involved in HDR UK, coordinating the applied analytics theme and the Scottish node for HDR UK. And my background, which is important for this one, because you'll see as I go through the slides, is in doing things with computational logics. And so I thought for this, since this is the first time I've actually done one of these seminars for HDR UK, despite having been in the audience for many of them, I thought I'd take a little bit of a risk and try and say something about generically what I think we're doing with this sort of data sharing and view it from the perspective of computational logic, which is unusual these days, I think, because mostly people kind of dive in and do stuff with machine learning and whatever. They don't really take the kind of broader view. So you're either going to really like this seminar or you're going to really hate it. I'm not quite sure, but anyway, we'll see how it goes. Let me just step forward if I can. Oh, I'm immediately in trouble. What's happening? Oh, well. Right, so a little bit about what this talk is about and what it's not about. So it's about precision medicine, as broadly as I can make it. And I think looking at it from a logical point of view helps to highlight what I think of as the kind of inescapable challenges, whatever you do, whatever you try, whatever system. I am going to push on protocols to facilitate data sharing because it's something I know, and I'm going to argue that it's important and it's something that's not been appreciated enough. I want to talk a bit about what can and what can't be guaranteed for privacy when you're viewing things that way. And then at the end, I want to talk a bit about how that sort of thing scales to large scale. And there are things also that it's very important to understand that I'm not talking about. So often when people talk about AI, at least in my hearing in healthcare, they're really talking about machine learning, and they use it more or less interchangeably. For me, machine learning is great and hugely important in all of this, but it's just one of the basic elements. The talk I'm going to give will be pretty much agnostic to what sort of inference you're doing inside your system. And it's actually mostly also agnostic to the choice of infrastructure you use. So it's going to be that general. So if you don't like that sort of general talk, you're already in trouble. So a little bit about terminology. Sorry, these slides are busy, but I wanted to get everything very precisely on the slides. For some of you, this will be completely obvious, but I just wanted to run through it because in my experience, people get this wrong. So when I talk about axioms, I mean some set of statements about a system. And I tend to, since I'm a logician, I tend to use implication, conjunction, and that sort of thing as the operators to connect things. And when I talk about a logical conclusion, I mean something can be derived using the rules of inference of that system. So that's what a logical conclusion is broadly. When I talk about deduction, I mean when you've got a set of axioms, it's something that follows using the laws of inference from the axioms, and you derive a conclusion. So you go from axioms to a conclusion using deduction. When I talk about induction, it's the other way around. You've got a conclusion and you're hypothesizing what the set of axioms might be that would allow you to derive that conclusion. So machine learning systems typically are inductive systems. They work from conclusions to axioms and generalize the axioms as far as possible. When I'm talking about abduction, which you don't hear about so much these days, I'm talking about something slightly different. That's where you have a conclusion and you've got some set of axioms, but not enough to derive it. And so you need to take and derive an additional set of evidence that along with the axioms would allow you to derive the conclusion. That's what abduction is about. And you'll see in a moment why that's important. And then when I talk about protocols, I mean some formal structure, and I'll give you a specific one that describes the sequence of interactions that you allow between agents in some interactive system. So these are very generic types of things. They're not specific to healthcare, but that's what I mean by a protocol. Okay. So here's the way I think about precision medicine viewed as logical inference. Now, I've made this as general as I could possibly make it. It doesn't cover everything, but it covers quite a lot of things, I think. And the basic idea is if you start at the bottom left with a person, you have a bunch of assumptions about the person, the hypotheses you have about their what's with their condition, the therapies you might have in mind, and so on. And you have a bunch of observations about them, their genotype, their phenotype, etc., etc. And then moving across, you use that by some means of similarity, which I won't be talking about much in this talk, so that will remain a process of mystery. You derive a cohort from the population, where you're matching the observations that you've got onto the cohort that you're going to derive from the population. So then you have a bigger set of observations derived from the population. Then you up on the right-hand side. Then through a process of abduction, you derive a model that accounts for the observations. And that's as generic as it turns out to be, given whatever system you use. So now you have a model, the thing highlighted in yellow. That model is then used in the process of abduction to form a union with the observations that you've got. And you cycle around. So that's the kind of broad picture of inference that I'm going to use throughout the talk. And you might disagree with it. Certainly, it's not very detailed. But I think it's an interesting broad model. If you look at that, at the very top level from the kind of protocol side of things, then if you look at the left-hand side of this slide, then you've got a kind of recursive thing going on from a person with some observations, this observations P thing, and you derive the observations from the population, and then you construct the, the model from the observations, and then abductively, you build the assumptions in consistent with the model and the observations. That goes into your description, working description of the person, and you cycle. And the interesting thing about that from a logical point of view is no one single step in that protocol is deductive when explained in this way. Sorry, which doesn't mean that deduction might not have been going on somewhere in the production of all of this. Of course, it would have done. There'd be loads of things you deduce as part of the underlying system for this. But the basic form of inference that you're using here is not deductive, which if you're a computational logician like me, tells you a lot about the sort of system it is. If you look at the right-hand side, here are some of the things that I would observe. So the observations you've got are dynamic. They change during the recursion. The ontologies we know are dynamic. The matching we know is imprecise, given the observations. When you derive the model, because that's not a deduction, you have many models that could account for the observations. Since your choice of assumptions is not deterministic, there are many sets of assumptions. And in your recursion, the assumptions may later be invalidated. So it's not a monotonic inference that you're doing in this sort of system. So that, from my point of view, I prefer deductive logic, is almost the worst possible case for deductive logic. Everything is fluid. And that's the reason why, in practice, we're likely always to be limited to really quite specific protocols in practice. Having a generic protocol like this one is going to be actually useless in practice. So here's a more specific protocol. So same underlying system. And the way to understand the protocol I'm suggesting is the way you bind inference across the different actors in the analysis that you're going to do. So there's somebody, actually, that looks a lot like Kathy Sudlow. And up there is textually a description of her protocol in this particular case. So I've just invented this protocol. I'm not claiming generality for it or anything. So she needs a curation site for a cohort. So asking a curation site for a cohort based on the observations she's got. Then she gets back a cohort data set from the curator. Then she requests a model for the cohort data from the inducer service. Then the model arrives. Then she requests assumptions based on the model from some prediction service. And then the assumptions arrive back to her. So these yellow things in the textual protocol are things that come from the model I already described. And I can formalize that. So there's a formal version of this. So this is the first time you've seen this kind of formal notation. You don't need to remember really what it is, but what it is a language called the lightweight coordination calculus that We invented in Edinburgh really quite some long time ago. The only important thing about it really is that you can do arbitrarily complex computations in predicate logic through the constraints that are attached to the various message passing elements in the protocol. An arrow with a double symbol going to the right is a message going out. Arrow to the left is a message coming in to, in this case, Kathy is the experimenter. So it doesn't matter if you don't understand it in great detail, but I hope you get the kind of gestalt feel of what these protocols look like. The important thing for the purposes of this talk is that that's what Kathy sees and can manage and is specified as what she wants to do with the data that she needs to acquire for this particular experiment. Of course, you can do the same thing for the other people that she's going to have to interact with, the other services. So for the curator, for example, so the curator has a different constraint. There's somebody who looks very much like Sushil when he had a beard back in the day. And he's going to receive a request from the for a cohort and then send the data if he can find the data. So that's the formal version of this. Same thing for the inducer. So there's somebody who looks a lot like Aidan Doherty. So the same sort of thing, gets a request, sends the model when he gets the request. There's the formal version. And there's somebody who looks a lot like Hong Han Wu doing the prediction bit. So receives a request for a prediction from an experimenter, then sends the assumptions that the deduction can get done. And there's the formal version of that. And you bring all of that together, that's the entire protocol. And often people write down protocols like that using this kind of bubble diagram on the right. So the blue things in the diagram are the agents, and the arcs in the diagram are the messages being sent or the interactions, depending on the sort of system that you're using. So that's the sort of model you use for describing this kind of protocol. Okay. And I think there are some important points to understand before I go on saying a bit more about this sort of thing. So the way to understand these sorts of protocols is, I think, in this context, different ways of understanding it. I think the best one for this context is it's a formal contract between the agents that are going to have to participate in supplying the data for the experiment. And then running the protocol is like rewriting the contract as the computation unfolds. Imagine you have a contract, and every time you have to do something stipulated by the contract, you write it into the contract itself. So now it's a new and more specific contract, but still consistent with the original one. And you just keep doing that until you're finished rewriting, and then you've discharged the whole contract. So that's, I've just given examples there of the sort of rewrite rules that you have. You don't need to understand these at all, actually. It's just to show that it's basically a rewriting system given a condition, and that's enough to be able to describe the semantics of these sort of, at least the operational semantics of these sort of protocols. So what that actually means is that you have, if you have the sort of protocol which can be linearized, which covers an awful lot of the things that people want to do, then that protocol can be held anywhere. It can be on a web page, or a message, anything that can hold state, can hold the protocol as it's being rewritten. And the reason that's true is because the protocol itself holds all the salient conditions relevant to the current and future interactions. And then what synchronization means for these sort of protocols is just being the next agent to successfully rewrite the state. So if you look down at the bottom of this slide, there's one other important point that I want to make. This has nothing much to do with whether the data is federated or single data source, because if I take the protocol, the one that I used for, I've just taken Kathy's bit of this protocol, the one for the experimenter. So you've got site 1 and site 2 and site 3 in here. That protocol would be running federated if those sites were different. So you're federating data from 3 different sites. But if the sites were all the same, it would just be inside a single data source, single trusted research environment. And so talking about things like this in the context of the protocol, knowing that you have a formal protocol to look at, surfaces a lot of the issues of data leakage and allows you to look at them and analyze them, whether it's federated or whether it's inside a single trusted research environment. So let's look a little bit at data leakage and what that's like in these sort of protocol systems. And I'll make a few general points about data leakage on the way through, which is really my purpose in giving you this. So this is the protocol that you've already seen, the bubble diagram for the protocol that we developed. The green boxes are the bits where the particular entity knows about it because they originated the data. So for example, Kathy knows about the set of observations because she originated them. Sushil knows about the data set D because he originated it. The bits in the reddish boxes are the things that that person discovers, or that service needs to discover. So for example, Sushil needs to know the observations in order to originate the data set. Aidan needs to know the observations in the data set in order to construct the model. So that's the information that people need to know given this particular protocol. And I hope you can kind of roughly understand how that must be true, and you derive it from the original protocol that I showed you. So just following these through now, what might worry me as the person, I suppose I'm the person being talked about, what might worry me about this particular set of information? Maybe it's a problem if the observations that Sushil gets identify me. He gets observations from Kathy. Does that identify me? Maybe it would worry me if Aidan, if the data set identifies me. The data set he got from Sushil identifies me. Actually, he gets it from Kathy, identifies me. Maybe it's a problem if for Hong Han, if the model could identify me. And maybe it's a problem for me if that a single person, Kathy, knows all of these things by the time the protocol is finished. So these are all things that might give me concern about this protocol. So let's look at each one and think about what we might do about those sorts of things. So for the first one, Sushil, the observations, could we fix that in general, that I wouldn't have that problem? And I think the answer to that is no. I think most people here will not be too surprised by this, but I think it is interesting to work through why. So it's easy to think of counterexamples, and they all typically, they don't all, but a lot of them rely on simply knowledge that's outside the system that can identify people. So this is kind of simplest one. So if in my data set I have that person P has been appointed to a lecture, I know this is not a healthcare example, but it's a simple one for me to give. Year of appointment to a lectureship for P is 1988, and I know that the year a PhD awarded for P is 2000, then it is just people at Edinburgh know that I'm the only person around here who got a lectureship before he got a PhD through an accident of fate. And so knowing that, somebody at Edinburgh would have a very good sporting chance of identifying me. But as Sushil isn't able to know that. Well, he does now if he's in on the seminar, but he wouldn't otherwise because it's just part of common knowledge. It's not anything that he can reason about in the data set. So, of course, the standard response to that is obfuscation. We'll fill it full of data so that you won't be so easily able to recognize things like that. But then we lose some conclusions from the data. We lose in this in-depth understanding of each data point. We don't have the ability to track through interesting cases, like finding out what else about me is unique, and so on. So I think the general answer to this one has to be no. We can't really, in general, protect against this. Okay, what about fixing in general for the broader data sets? So the problem that maybe Aidan, given that he's been given the data set, might then be able to identify me. So here's another one. So if I know the date, maybe from the observations, we know that the date of birth of person P is 1962. So that's something that came in on the observation set to Aidan. And maybe in the data set that Aidan got, he knows that P has sister P2. So some other person, P2, this other person has a son, P3, some other person, and the date of birth of P3 was 1960. And people at Edinburgh, at least some of them, know that I was an uncle at birth. I have a very extended family, so my sister had a kid before I was born, and so a query like the one that I've just I won't give you. You can read the query, and a query that basically encapsulates that information is very likely to identify me. Not guaranteed to identify me, because there are other people like this in the data set, but there won't be too many, we know. So the important point about things like this, I think, is that we're basically bringing increasing amounts of knowledge into play. And that's what the data set allows us to do beyond the observations. And the horrible thing for precision medicine is that's exactly what we're trying to do in precision medicine. We want to bring in more and more knowledge. So we have an unavoidable tension between acquiring knowledge and revealing unique properties of people. So the answer to can we fix this always and in general is, I think, no. Can we fix it in general for models? I think also models are obscuring more, but I think in general you have to say no, not in general. So because you can think of cases where you can't, or at least you can't be sure. So if the model generalizes from the data set that you're given, so it gives the same answers, plus maybe some more created through induction, admittedly, then it can answer the sort of query that I gave you before about my sister and what offspring they had and so on. And if I know that that uniquely identifies me, then I can then ask exactly that same complex query, plus whatever it is that might be compromising to extract more compromising information. So without some other forms of protection or inspection, I think the answer for that has to be no. You can kind of see what I'm working towards here. Basically, every time anybody thinks of a generic mechanism that's going to protect against data leakage, we can always play a game where we can find something that subverts that. And I think that tends to drive us towards very, very close inspection of the actual protocols themselves. So the fourth bit of this was avoiding experimenters knowing too much. And I'll talk a little bit more about that because it's closer to the individual protocols itself. I'll give you 3 ways of doing that. So here's method 1, which is the most direct one. You revise the protocol. So if you look at the protocol in the middle, that's the one you saw before. That's the one where Kathy knows O, D, M, and A, the observations, the data, the model, and also the assumptions. But it doesn't have to be that way. I could have a revised protocol, which looks like the one in the top right, where Kathy will only know O and A. And the very simple trick that's pulled is not to route things through Kathy. You simply route them through the other entities. And because you've got a generic protocol language that encapsulates all of the things that the different actors have to do, you can play that trick. So that's an argument for having the sort of protocol language that you've seen. So you can do that, just adapting the protocol. Of course, then you're in the realms of building very, very specific protocols with very specific security constraints. Another thing that you can do that's more generic, that works for some of this, but not all of it, is to control the data across the protocols. I'm not going to go through this in detail. It's bristling with the maths. The horrible looking mathsy thing on the right-hand side is actually the operational semantics for the protocol language, which, remember, I gave you a little taster for at the very beginning. And the bits in red are the extensions to the operational semantics to do a form of type checking on it. What the type checking does is it looks to see whether the data that you're moving across in the rewrite is something that you are permitted to release. So it tests on whether it applies constraints to the data that you move as you do the rewrite. So for example, for the curator, Sushil is the curator. Suppose this is a particular bit of your protocol and you've been doing rewrites. And so you've been asked for a cohort and it's A1 and A2 are the observations that's come in. And then Sushil is going to generate the data set D sent to Kathy as the experimenter. If you've got similarity from A1 and A2 to D, then if similarity A1, A2 to D1, D2, and D3 holds, then we test whether that's safe to release before you do the transition to your new state. And those sort of checks are ones that you can enforce in the interpreter for the protocol. So it is a bit more generic. Oh, and by the way, at the bottom, if anybody's at all interested in this, I've started putting in at the bottom references to the papers where these sort of techniques are described. Next thing, third thing that you can do is model checking. So I don't want to get into this in detail, but the basic idea is suppose Sushil as the data curator has a choice of protocols. You could either use the one on the left or the one on the right. You've seen both of them before. And he has to decide which one doesn't actually release data to the experimenter. It's the one on the right, as I explained before, because D never goes anywhere near the experimenter. That sort of thing and many, many more complicated properties of protocols can indeed be checked by doing model checking on the protocol. So model checking is just a way of automatically inferring properties of the protocol. And it turns out that that you can't do this for everything, because it's not possible to model check every possible protocol you could ever write. But for a big class of protocols, this is very effective and actually practical in real time. Anybody who's interested can look at the paper at the bottom. So that sort of technology can be used. And the nice thing about the model checking technology and also the change to the interpreter technology is that, like everything else I've been talking about, it doesn't care whether you're in a trusted research environment or you're federated. It only cares about whether you're using this sort of formal protocol. Okay, so what does that mean for automation and trust? So I don't know if this works for you, but it's my best attempt. And again, there's a paper at the bottom if anybody's interested. So I think one of the things that this allows you to do is to automate a lot more inside the TREs, if that's what people want it to do, or even automate on the federation aspects of it, if that's a better way of doing it. But the important point is, inside some trusted enclosure, you have protocol specifications that you have created and are available to be selected and can be completely automated. The protocols themselves, and then approval is by class of protocol. You create these protocols as generic as you practically can, and then when you design an experiment, you're really choosing a protocol to run. When you run it, you create an instance of the protocol that has, along with it, the data that it generated. And then data managers, because of all the problems in completely automating assessment of data leakage, must check it. That problem has not gone away, but that goes on inside the trusted environment, with the resulting data then being released for people who want to explore it in by whatever trusted means is stipulated by the TRE. So that's a lot different from what we'd have, say, in Scotland in the data safe haven at the moment, because experiments run automatically and the data controllers are checking results rather than deciding on which full protocols can be trusted initially and then running that. And the important principle that it's exploiting is the testing bit. You're testing on an instance of a protocol rather than trying to prove general properties of a protocol without the instances. So it's an easier task to be able to do the checking mechanically because it's an instance. So that's broadly and very, very quickly what this sort of thing should do to automation and to trust. What I'm not saying, just to be completely clear, is by doing all of this automation, everything now works and it's completely automated. Not at all. It still needs to be checked and all of these sorts of things. Some of that checking is human judgment. All I'm saying is that it's faster if it's done on instances, and the way to get an instance is by using the generic protocols, running them quickly inside a TRE. So that's the bit that's kind of close to what we currently do. And then a little bit about what that might mean if you went outside a trusted research environment. This is really pushing it well beyond what anybody, as far as I'm aware, currently does. But it's the sort of thing that we have been doing for many years with these kinds of protocols. In fact, I put the original paper down there since 2004, actually. So this is in a way pretty old stuff, but you don't see it much used in healthcare. So the idea is, because these protocols are device independent, I can stipulate you very precisely what the protocol language is, but the implementation of an interpreter for that language could be on all sorts of different kinds of systems, all sorts of different ways of defining state and so on and so forth. So they're device independent specifications. They don't care which agents are using them. So you can distribute them to loads of autonomous agents if you want. Those agents have to be able to interpret protocols, though. They do need some software to do that. And those agents could be outside of trusted research environments. Of course, you have to take great care then what protocols you write, because that problem has not gone away, and as I described, will never go away. And then the idea is, suppose you're the agent down at the bottom end of this thing, and you've got some protocol you want to enact. Then you send it to the relevant agents with the interaction specification and the interaction state, and then that can get routed through to the other agents with the different states, back to you with whatever states and whatever additional information you should have received. And so you can play these sorts of games in more open systems, and there's a whole literature on how to do that sort of thing very openly. It's not a panacea. You need to be careful how you do it, but a lot is understood about how to do that sort of thing. So that's the kind of basic idea that I'm just going to develop for the next few minutes to give you a flavor of that. There's no time to get into this in very much detail at all. When you do that, then the other thing you get into is this thing called social computation. And the idea of social computation is, if you imagine that many social systems that are around here, in social systems, you're using people as well as automated systems for doing some of the computation. And so if you imagine this as being something that's on two axes, you have these social systems, and on this axis, on the x-axis, you have more and more social systems. You're using the power of the agents involved in your system more and more. So you do a lot of that, but typically it's not very computationally complex beyond what's going on in people's brains and that sort of thing. And the y-axis is conventional computation, where it's very complicated, sometimes algorithmically, but doesn't involve society very much. And there's a whole space of things that's could be inhabited in the middle, where it gets more complicated computationally, then is also very socially involved. And that's the sort of thing that people talk about in healthcare when they're talking about using, I don't know, Fitbit data or social data for being able to acquire different new types of, say, phenomic information. And so you're interested in that kind of space. But when you're interested in that kind of space, the thing is, what you need to worry about with the protocols changes a little bit. And I'll give you just a couple of examples of that. The ones I'll describe are the ones that are highlighted in yellow here. I've already described two, of course. So I already described a bit about controlling the transfer of personal data, and I already described a bit about security. So those, importantly, the way I describe those two things apply just as well in these open systems as they do in more closed TREs. It doesn't matter because I was just talking about the protocol. But I'll say a little bit about things that the things in yellow here are things that come up specifically in these kind of broader open system. One is to do with mapping many ontologies, because in open systems, you don't get to choose which ontology you're using. You have to use the ontologies that these other systems you're interacting with use. So healthcare is pretty bad, but the most extreme cases where you just have many ontologies, you have to work out on the fly what the mapping might be. So that's the hardest version of this. And the other one I'll talk about a little bit about is using the social behaviors themselves to improve reasoning performance. In other words, when you know nothing much about the agents that you're being involved with, other than what they do with respect to the protocol. And interestingly, knowing those things can improve the reasoning performance on the algorithm that you originally had in mind. I'll explain those two things. The only reason for doing that is just to give you a flavor of this kind of stuff. Okay, so first one is the ontology mapping. I just have one diagram for you. The paper, as usual, the paper is down at the bottom if anybody's interested. So the idea of that is, if you have two agents, these little blobs here, one with language L1, and the other one also uses language L1. So they both use the same native language. But out in the big wide world of all the other things they might interact with, there are different languages. But if that the one on the top left here, using a language L1, is clever enough to interact with some of these other different languages, and forms mappings, then if the second agent is using the same protocol, the same model of interaction, then there's a very high probability that it will be able to use very, very similar mappings, because mappings between ontologies tend to follow fairly closely the interactions in which those ontologies were used. So it's a little bit like using a sort of, in the natural language world, one of the things that's been very effective is paired corpus ontology mapping. So paired corpus natural language processing. You know you're working on the same corpus. It happens to be in a different language. You use the fact that you know it's the same corpus to be able to work out the mappings. Same thing applied here, but for the protocols. So this is one way of being able to drive that kind of protocol mapping to its, what I think of as its kind of extreme, when you really genuinely don't know in advance what the mappings will be, but you do know what the interaction is supposed to be. That's that one. Another one, which I think is even, at least to my mind, is even pushing it even harder, is where you have, you look at just at the performance of the different agents that you're using in your system, and you use the performance itself to be able to improve the algorithms. The one that we looked at was this thing called peer ranking that we developed. And peer ranking was a means of giving a reputation to the agents in the agent system based on how well they performed in the interactions. So you've lots and big system with loads and loads of agents, loads and loads of interactions. Some of them will work very well because the agents work together very well. Some of them will work very badly because for some reason the agents are incompatible or the solution isn't good enough or whatever. So forgetting about the details of all of these things, simply saying, do they work or do they not, enabled us to have a thing called peer ranking, analogous to page ranking in web pages. So the idea is that you can gain reputation by linking to, in this case, peers, agents, that already have high reputation by being good at doing interactions. And so we used that peer ranking algorithm with a bunch of agents doing machine learning tasks, so basic machine learning tasks, to try and see how close we got to the performance of bespoke ensemble learning mechanisms. So taking different machine learning systems and trying to produce a better learning system through the ensemble behavior, collective behavior. To our surprise, the performance was really quite comparable. Simply by taking a peer ranking algorithm, building it into that agent system. So it's a good example of something where you're taking a generic way of managing reputation between agents, using that generic measure of reputation to be able to improve the performance of a specific type of algorithm. Right. So that takes me to the 40 minutes, and in the last 5 minutes, I really just wanted to say a little bit more about these sorts of systems, and just give pointers to various people. So that there are many things I can't mention in this talk that are relevant to this, because you can use this sort of approach for loads of different things. Some of it's been an application, so we did a lot of stuff in astrophysics. And you can read the people who were involved. You can look them up on Google if you like. The interesting thing about the astrophysics stuff was we were pushing the actual computational performance of the protocol algorithms, because that was back in the e-science days, and we were working with a system called AstroGrid, which was doing manipulations on astronomical images. So it was a very good way of. Turns out that the protocol language, in some cases, to my great surprise, is more efficient than bespoke languages for doing that kind of thing. No time to go into the details here. We did some work in proteomics, which I'll just mention that we did it. I don't have this time to describe the details. Of course, we've done loads of stuff in healthcare. Also did stuff in business process modeling. Interestingly, using these kinds of languages. We even did trading systems for these languages. Guo Li working down in Imperial did some interesting work there. Did quite a lot in adversarial systems where people are trying to undermine the way that you do the analysis of the protocols. Did a lot of work on open data with Nigel Shadbolt and other people in the Open Data Initiative. I've mentioned stuff on ensemble learning. We also did some stuff on evolutionary learning there, interestingly did quite a lot of stuff on argumentation, where what you're trying to do with a protocol is actually not to capture a protocol for data acquisition, but trying to capture a process of argument, like you might have in, I don't know, diagnostic reasoning. Also looked a lot at infrastructures, in particular peer-to-peer infrastructures for being able to deploy these systems, and I already spoke a little bit about security. So I think that takes me pretty close to the 45 minutes mark. So I will stop sharing, I think, for now, if that's okay, and open it up if anybody wants to. Oh my God, there's Flavio. So in the chat, hello Flavio. Shall I try answering these? Normally in these things, I look at them and I ask the questions. Now I find myself having to ask myself the questions. So I'll do that. That's okay, unless you want to do it, Serena. But I'll do it. So Flavio's point is, I suppose people can read this. So you're moving precision medicine from knowing individuals deeply to knowing diseases deeply, thanks to individuals, and then returning this knowledge to individuals, then creating a layer of data protection that prevents leakage. Does that capture the general? Well, yes. I sort of have 2 points, I suppose. One is that this sort of thing makes the process of doing inference with data in healthcare richer. You learn a lot because you have the protocols up there and you know what the intention is for the experiment or for the data sharing that you do. And so that is in line with what you said. And the other thing is simply to highlight some of the things that for me are just kind of basic inference steps that you can do that help a bit with things like data security, or make you view data security in a slightly different light. I don't know that was a good answer to your question, Flavio. I was going to ask you to ask it, but probably not. There's a lot of people on the talk. Oh, David. Hi, David Porteous. Gosh. Tension between precision medicine and privacy, an interesting one. Does this become more of an issue for PPI and trustworthiness? Yeah, I think it does, David. Actually, but one of the things that, to be candid, I think one of the things that worries me a little bit about the way some of this is going is I think it's very easy to believe that it's a process of magic that kind of goes on once you're fiddling around inside TREs, and you can apply various functions that will obfuscate data and all this sort of stuff. And I just find it so easy to think of counterexamples where that doesn't work very well, or at least couldn't be trusted to work very well every time. That I do think we need to understand more of it at a protocol level, just because that makes explicit a lot of the things that you can then use as levers for people monitoring these kinds of things. That's not a new idea at all. People working in database query languages understand this, and it's the reason why they try to build now security features into database query specification languages, exactly so that you can surface the issues that are security issues inside the language that you use for querying the system, rather than just having them be kind of understood as being solved through a process of magic. David, I fear we promise something IT or we can't deliver. We can't deliver, it all falls apart. Yes. So I personally don't think it makes an awful lot of sense to think of something being completely, there is no sense of complete trust in any system I've seen that I would care about in healthcare for 2 reasons. One, because it's too easy to bring external knowledge to bear, which you saw in the examples. And the second one is the whole process of experimentation drives you towards detail. And I do not see how you would last for long doing really interesting experimentation without having to face those 2 problems head on. Which is not to say that you can't have trusted research environments. It's just that you can't encapsulate all of that algorithmically, I don't think. Oh, Hong Han's got his hand up.
2 hands. Oh, there was Peter first. Sorry, Dave.
Oh yeah, you do it, Serena. Where's Peter?
Hi, thanks very much, Dave, for your talk. I think my question probably follows on from David's. So in my life, I think there are several members, people working professionally, whether it's doctors or others, who I place my trust in. And my question is, why should we not trust researchers to keep people's data private and not to exploit potentially being able to identify people, for instance?
Yeah. So I think you should. I actually, maybe that's something I should say in my slides. I think the last line of defense is always the person, right? And the thrust of my argument with security is you will eventually have to have that last line of defense. It must end there, because there isn't. I haven't given you a proof because I'm not sure I can give you a mathematical proof of this. I can give you plenty of counterexamples against the kind of standard arguments for preserving security automatically. In the end, it is going to have to be an issue of human trust. And I think that's the right place for it to go. I don't even think that's a problem, because I think if you look across HDR UK, these are perfectly competent people to work with sensitive data on the whole. The structures there can be built into the contracts that we establish with these people. We can have the necessary legal recourse, etc. The problem isn't really that. The problem, I think, is moving fast enough within those constraints. The problem at the moment isn't that we aren't reputable. The problem is that we're slow, and it's getting the right kind of automation in that I think is important, rather than hoping for some kind of panacea that will save us all from this. I don't know if you agree. We could have a big whole point about surfacing this in a kind of logical way is just to be able to have the argument. I'm perfectly happy to be wrong.
Thank you.
Hong Han, you next? I don't know. Serena knows. I'm going to choose you.
Thanks, Dave. I really like your talk.
It's just because your face was featured in it. I hope you don't mind.
Yeah, I really like this abstract level of all these components joined together. That's a really kind of eye-opener for me about TIE using these abstract level stuff. Oh, yeah. And just one question about this deduction. You said there's no point in deduction in your whole flow.
Yeah.
If we add deductions that, for example, we have a model, we're going to using this data for validation. They're actually doing deduction. Is that right?
You're right. So this is a good question to ask. So and it is a bit confusing. So you could imagine having something whereby inductive and abductive and all of these distinctions, and underneath there's a pure deductive system. I'm a computational logician. I love a pure deductive system under everything. And of course, from that system, it's so malleable. You can build induction, you can build, but sort of the point of my examples is that regardless of what's underneath, it's still abduction. You're still hypothesizing something. And because you're hypothesizing something, it could be defeasible. So the thing that you assumed could turn out not to be a deductive consequence of what you later derive. I think that's very common in medicine. It's very, very viewed as purely a piece of logic. I don't think not much that I've seen I would consider to be just pure deductive. It would always follow in medicine. I think, and going back way, maybe 30 years ago when I first paid any attention to this, there was that hope that it would be all deductive. There's the Oxford system of medicine, I remember. The idea was to be a big deductive system. We deduce all of everything we needed to deduce. And it can't work because it's not all deduction. Which doesn't mean that you can't implement it in a system that uses pure deduction, because computation, at least for me, is deduction. So you know what I mean? It's that kind of thing. On the other hand, oh, you got me going now. So on the other hand, I do wonder whether when you get close to the point of clinical care, it might be deduction.
Yeah, exactly.
That would be great.
Apply this as deduction, right? Yes.
Yeah, that would be great. Because there you do want it to be deductive, because you'd really like to reason about consistency. And you'd like to reason about it in a hard-edged way, where you say, is it consistent or not? Whereas in the inductive systems, sure, it's a concept for implementing them, but it's not the way it's not the thing you're reasoning about. Sorry, I'm not very good at explaining this, but I think you probably understand it better than I do.
Yeah, actually, here comes my question.
Oh no,
the real
question.
So you said the model actually has this risk of always has this risk of leaking information, right?
Yep.
So I was thinking the array round whether we can make use of this property of this model leak information to share the data, some level of this data, like insights from data, to whoever in this, in somewhere cannot access the data themselves, so that you can avoid share data directly by share the model. Like people can use the model to derive insights, which not necessarily from your model can help them to do this. I'm asking this because one of the experiments we have done recently is, have these literature published the models combined together, which can do a better job because different models derive from different cohorts. And this model itself actually captures, for example, all white people from United States, and model from China is all the Chinese people. And for the same disease like COVID-19, you have this power to combine a different cohort derived insights together. So this is the experiment we have done. We proved this worked for COVID-19. But the question, more general question is that possible at all? We can share the insights of the data sets through the model. So it's the other way is not prevent data leakage, somehow, do this kind of stuff.
Yeah, I think so. So since your models, if you derive them by inductive means, they will generalize. So in that sense, they're a little bit safer than going to the data sets themselves. So I can do clever things by trying to get probing queries into the model to extract specific information. But even then, you're protected a little bit. Even the example I gave, I didn't say it in the example because I want to get on, but if it's a generalized model, it might have returned more answers than the ones originally in the data sets, in which case then it's likely to obfuscate, I guess, from the data that was originally about, say, me. So that's a good thing. The problem is being able to rely on that, but that may not be an issue in practice. If you've got the right kinds of models generating the right kinds of data in a constrained way for a particular domain, then you're in business. That comes back to the issue of trusted researchers doing the right engineering. I mean, it is an engineering task. It comes down to, did you engineer them specifically the right way for this type of data set? But it's a brilliant way of, I actually have thought in HDR UK, it would be a really good way of getting people who are interested in the data closer to it, but not amongst it in the way that you describe. That'd be a brilliant way of doing that. And I've not seen an awful lot of that done, and it'd be a fantastic. It's almost like a product of HDR UK. I don't mean product in a commercial sense, product in the sense of something produced from the effort itself. It could be more valuable than data sets in the sense that it's more portable. Yeah, I agree. It's a good idea. But it has to be constrained because the models themselves can't be guaranteed not to reveal. I think.
There is David and then Sushil.
David. Why don't you talk, David? So I missed the sound of your voice.
You're missing the sound of my voice, Dave, because I've got somebody who's drilling holes in a wall below me, and it's a racket in the background. That's the reason. You can probably hear it coming through now. It's a relatively quiet day here in Edinburgh, but it's been battleships, so that's why.
I see.
So apologies for that, but a great talk, Dave. Very stimulating. I think it's raised some really interesting questions, and I was thinking just now about the reciprocity here. You look at patient P, and you look for the best match to your data set. And what that does is actually to reveal something about the best match in the data set, which previously was an anonymous component part of that data set. Yep. So there's a two-way process here, that in finding the best match, you also find the person most like the person that you're using as the test subject. And I hadn't really thought about that before, but I do think it comes back to the point that Peter Charlton raised, I think it was, that actually what we have to do more about is to explain why we do things and also explain the process we have to go through before we are allowed to do them. That is the review process that goes on at multiple levels about the ethics approval and the access approvals that go alongside this process, which is all geared towards public benefit. If we don't do that, I think we start to hit problems because we will fall down on external scrutiny.
Yeah, I think that's right. I think for me, looking at the formal aspects of the process, if for people who are prepared to embrace the formality of it, then there's really two types of scrutiny. One is when you look at the generic protocol, unused, never touched data. There's quite a lot you can infer about these protocols, what they will transmit, what they won't. And you could imagine excluding protocols on the basis of that analysis. You can do it by hand, or you can automate various bits of it. And that would trim down, that would give you a certain sense of confidence for generic protocols for doing this, but it wouldn't be perfect. Because it might be you have a generic protocol that looks good when you analyze it separate from the data, but is then pathological for particular data sets. But then I think the other equally important, possibly more important thing is forms of analysis. Once you've run the protocol, you've seen what the data is, you've seen what it did. Maybe nobody else needs to see that if it's a protocol that can be run automatically inside a TRE. But then you use techniques over the instances that you've then got. And usually it's easier to reason about instances than about generic variables. And so that would give you a second line of defense. Neither of those two is perfect, of course, because you could find examples, because to be perfect, they would need to be on generic protocols, they would need to be able to do generic computations, and these languages aren't decidable in general. So it's never going to be perfect, but you get very high levels of assurance, perhaps. And Honghang's point about the models is also germane. So same sort of thing applied to the models you produce. I think that would be, that sort of analysis might be very effective.
Dave, I'm conscious
sorry,
about the time, so people is dropping.
Yeah, we gotta go. Anything else I should pick up? I think there's various things in the chat that people will have picked up. I'm trying to see if there's anything else I need to answer before, but it is 3 o'clock. I think we got the most of it though, actually. Did we? I think, Serena? Yeah. Good. So normally what I do at this point is to thank the speaker, but I'm the speaker and I can't thank myself. That's
thank you, Dave. Everybody.
Thank you.
Thank you
I'll thank everybody else for putting up with me. I'll thank everybody else for putting up with me. Normal service resumed with proper seminar speakers. When's the next one, Serena? Do you know?
Is on the 26th of August, and the registration link is in the chat.
Yeah, fantastic. Thank you very much, folks. Enjoy the rest of your day.
Thank you.
Thanks, Dave. Bye.
Bye-bye.
Bye-bye. Bye-bye.
Yeah, thanks, Dave.
Bye.